Okay, I wanted to talk about manometers a little bit, and this is you're going to see a problem on manometers in the quiz one. Okay, so this will be like the problem from chapter one. Will actually be a manometer problem. Okay, so basically, what is it? A device that measures pressure due to a variation in height of a fluid. Okay, and here's a simple example of it. All right, so you have a simple, just a U-tube containing some fluid in there. And what will happen essentially is the force due to the pressure of this gas will force the liquid down on this side and cause it to rise on the other side. And depending upon the pressure, then you would have a difference. You know, if it's a lower pressure, it would force down less, and if you have higher pressure, of course, it would force it down further. Okay, so we're going to use that concept to actually figure out, knowing some characteristics of the liquid in our fluid. In general, you could say fluid, but our liquid, in this case, to determine what the pressure is of this chamber, of this gas that's connected here. Okay? All right. So here's a basic diagram of the problem. And so you have some gas here connected to a tube, and you have some other, these are points, like this is a point, this is point 1, point 2, then you have some elevation between here and here. And here's your other fluid. Okay, they're using the change in that to determine the actual pressure of the gas. So we're looking for the pressure of the gas. Okay. So one of the things when we first start off looking like at a problem like this, what we'll recognize is that, in this column, if you're at the same elevation, you're going to have the same pressures at any point that's at the same elevation. So pressure 1 and at 2 is the same. Okay. Then the next thing is, since we have that, what we're really looking for, we're looking for, essentially the pressure here, right, at point 1. The pressure would be the same everywhere. So anywhere along this, inside this chamber, the pressure is going to be the same. And of course, this is kind of connected to it. So this is all essentially part of the chamber. Is that the pressure here pushing against this is essentially that, it's whatever pressure here is at, it's the same over here at 2. Okay. So now this is our change in pressure kind of as a function of depth, right? So this is our same type of thing that we looked at previously, where we're talking about like the problem with the dam. The water pressure of the water is forcing down, and you get pressure. The pressure is the same everywhere. So it's due to the weight of this column plus whatever pressure is in the atmosphere essentially pushing down on this. So you have those two things to add it together will give you the pressure at this point. So the equation essentially just becomes, here's our specific gravity times our height and our pressure of atmosphere, which is acting down here. Okay. All right. So take a quick look at an example. Okay. So in this example, they're actually using SI units, right? But we could always use USCS units or convert back and forth between the two. And you can, in this case, don't convert to USCS units because, of course, it's not giving you any USCS units. So if you can just come up with an answer that's in SI units, that's fine. And if it was in the case that you needed to have in USCS units, you would just have a final conversion that you would have to go through to get to that. Okay. So first thing is we're looking for pressure in the tank here. Okay. And we're given some quantities. And we have the height and the specific gravity. Okay, so we're not given like specific weight, but we can get to that from here, from the specific gravity, right? So if you remember, just going down through the problem, any assumptions? Okay, so the gas is really low. This is an assumption we'll make for these problems. And the gas is in the tank, pressure, the density is really low, so we don't have to worry about like its weight pushing down on here. The next thing is, actually, I shouldn't say that in all cases because we're going to look at some problems where we may have to, a little bit further, we may have to include the density of the fluid, all right? But that's a little bit further, at least at this point. When we're talking about a gas, we're going to ignore or neglect any any weight due to that gas. Okay. All right. So first thing is we're given the specific gravity of the manometer fluid. And what we're going to do is, since it's given a specific gravity, we need to find the density, right? So if you remember that it's just density divided by the density of water at 4 degrees C, which we know what that is. This is a given quantity, gives us this specific gravity. So if we're looking for density, of course, we're just going to multiply both sides times the density of water at 4 degrees C. And when we do that, we come up with 850 kilograms per meter cubed, right? And so the problem just becomes simply just, okay, we have the atmosphere pushing down, and we have, here's our specific gravity times that height, and then we perform the math or the calculations. And one of the things we need to recognize here is that we're given in pascals, okay? And so since we're in pascals, you can actually go through, the process. Pascal is Newton per meter squared, right? So we can actually go through this conversion process, which essentially, you might recognize right now that this is just a Newton, right? Kilograms meter per second squared, but the author chose to detail it out here. And here's the height, 50, so it's in meters, right? So it was 55 centimeters, which is just 0.55 meters. And then here's our gravitational acceleration, and here's our density. And since it's in kilopascals, we need to convert it, right? So 1 kilopascal per 1,000 newtons per meter squared, and that gives us just essentially the here's my 96 kilopascals. Here's my 4.6. Okay, 4.6 kilopascals is all this part. All right. So one of the things, a note of this is that the gauge pressure would be 4.6. Okay. This one's actually asking you to do the absolute pressure. Okay, so that's why we had this other piece that we had it added. If it was gauge pressure, of course, then it would be relative to the atmosphere, and then it would just be 4.6 kilopascals. Okay, continuing on. All right, so a couple other things. One is Pascal's law. Now, this is the reason why we can sort of jump from one point in the column to another one. And basic idea is that, with any change in pressure of like an enclosed fluid, you're going to see that same change in pressure in another location in that enclosed fluid. Okay. So we can apply that concept as we go forward here. And we could use that to actually figure out, let's say, the pressure at the bottom of this tank, right? So what we're going to have is, if we move upward or downward, we either add or subtract pressure, right? So in this case, if you're looking for this pressure at point 1, you'd have the atmosphere pushing down, plus the pressure due to the weight of this fluid in 1, and then 2, and then 3. And so we have each of those components individual. So pressure due to this component, pressure due to this component, and the pressure due to this fluid, right? So pressure due to this fluid 1, pressure due to fluid 2, and the pressure due to fluid 3, okay? All pushing down, all right? Okay, so we can start to use this concept. We'll take a look at another example here. And for this example, this is a little bit different because in this case, we want to measure, let's say, the pressure difference between these 2 points, okay? And this just describes it. So without knowing kind of what this is right now, this is just in general. We have 2 points. We have a point here, and we have a point here. And this is something else. I don't know, a nozzle or something, okay? So in this case, it's a fluid, so we have to include that in our analysis. We would need to include the weight of this fluid acting down here, okay, and here, right? Okay, so first thing is we're looking for the difference in pressure between these 2 points. Okay, so our equation just becomes, P1 minus P2, okay, is that pressure. So we do that just essentially starting from a point and then either adding or subtracting the pressures. Okay, so we start at point 1, and then we have the pressure, in this case, at A. All right, so this is due A. All right, so the pressure at A is going to be, P1 plus whatever pressure we get due to the weight of this column. And one of the things you're going to recognize, it really doesn't matter like how long this piece is. It's just the vertical height, okay, of the pressure, water, or in this case, whatever fluid it is. Okay, so that just is going to be A plus H, and we get the A plus H from essentially from this side. Okay, so what we recognize here is essentially this pressure at A, right? And then we go around, and then we look at essentially the pressure at B, right? So this is going in the other direction. Now we're climbing up. First we were going down, now we're going back up. So we're going to subtract it out. So in elevation, we're going back up. So we subtract out this part, the pressure due of this component. So at B, we subtract out this, the pressure due to the weight of this column from here to here, essentially. And we also subtract out the pressure due to this column, okay? And we needed the specific weight of this. So the pressure due to this column, part of the column, and the pressure due to this column, okay? Okay, we can go ahead and simplify this equation, right? If we take, P1 minus P2 is what we're really looking for, subtract both sides by P2, and then take everything else, put it on the other side of the equation by itself, and what you're going to recognize is this, like this rho 1g plus A, we have a negative term here, and then we have a positive term over here, so essentially those two cancel out, right? So this is gone, and then this part of the term is gone, and then we're just left with, rho 1 GH minus rho 2 GH, okay? And then we just break it out, pull out the G and the H, and then we have just rho 2 minus rho 1 minus GH, okay? And a couple of notes here, just the last one, you need this A to do the complete analysis here. And then if the density is very, very low, then this just, of course, becomes P1 minus P2 is just that the density of 2, which is this, of course, this fluid times G times H, okay? Because essentially what happens is that if this is really small, this term goes away, okay? So we'll take a look at another example here. There's a little bit more. So something, you could expect for the quiz problem on the order of this, something like this, maybe a little bit more complicated than this, but something like this. So example 1-10 is just a multi-fluid manometer, okay? And there's some given quantities as part of this problem. It tells you it's located at some height. All right, so that gives us our, essentially use that. So we use that for our atmospheric pressure. And we're looking to find the air pressure in the tank. So we're going to find this pressure of this air, essentially what's at this point here, right? And we have densities that are given for our different fluids. Okay, so just continuing on here. So the assumptions. So in this case, it's the pressure in the tank is uniform, right? And then any change in due to elevation is negligible, so very small. Okay, and then we're given the given quantities, properties are given for us, and then what we need to do is go through and derive an equation for this. Okay, so just taking a look at this example, and we're going to follow the same process as before. So in this case, we're going down by H1, and you can think of, like we said, it's all the points horizontal, right? So we can work on it from the perspective of thinking about it at some, relative horizontal points, right? So we go down by H1, we go down, and we have to take into account the the liquid. We go down by H2, and then we go back up by H3, okay? So in this case, it's just saying that it's the pressure of water, okay, which is here. And then this one is the, or not the pressure of water, I should say, the weight of the water, okay? And that gets added, so whatever P1 here, plus going down by H1, and then going from here to here. So you have the additional to that, what we're going to have is the pressure due to the oil, and then the pressure due to the mercury. Now in this case, we're going back up in elevation, so this is has a negative sign, okay, because it's in the opposite direction, right? So we go through the process. We just set up the equation. We're actually looking for P1, so we bring the other terms over to the other side, and we combine some terms because they're all multiplied times g, gravitational acceleration, and then we go through and substitute each in for each of those, and they show you this little, it looks like it's cut off here, but that's okay. This is nothing more than, this would be like, I think it's given in kilopascals. Yeah, we had to convert to kilopascals. That's all this part right here is showing you. Actually, there we go. So it's just converting to kilopascals. So if I just scroll back, then the final result is going to be 130 kilopascals. And just a couple of notes here from that. Pressure is the same in the fluid if you just jump horizontally, right? So we found that it simplifies it by just going straight across, and also that mercury is toxic, right? So, but we're not going to be making anything here, so we don't have a lab component, so we're okay with that. And just sort of a couple of final notes here. When you're looking at this part of the equation, and it's maybe like, oh, why is it the water here, essentially? What you recognize that if we had gone down here by H1, and we're looking for, if we had gone down by H1, what we recognize is we're using essentially, Pascal's law, that all horizontal pressures are going to be the same. So essentially whatever, whatever air pressure here plus whatever pressure due to the water at this point is the same all the way over here, okay? So we can even use that idea and go straight across to here, okay? So that's like the first part of the equation here, P1 and the rho water G H1. We're essentially just kind of going down here in the water and going like straight across to this point right here, because these are going to have equivalent pressures, okay? Then what we do is we include the oil, which is from here to here, and we add it because we're going down. And then the last part here, we're subtracting it because we're going back up, okay? So just some like final notes on this problem to maybe have you think about it a little bit more. So like I said, this something like this for quiz for one of the problems.